The light that okay, start.
Good morning, all of you. Today we shall discuss about the two topics which are very interesting and take a routine part in the normal functioning of the excitable tissues in the body. So, firstly, we shall start with the resting potentials or the membrane potentials. Then we will go on to see what is the definition of the action potential, how is the action potential initiated, and what are the changes that takes place in the excitable tissue whenever there is an action potential transmission going on, and how does the excitable tissue, maybe the nerve or the muscle, comes back to normal. Now we know that there are certain tissues in the body which are highly excitable and they are called as excitable tissues. The membrane surrounding such tissues is known as the excitable membrane, and whenever there is a change in the activity or the environment around this external environment around this membrane, it initiates certain changes within the nerve, and these changes within the nerve get or the muscle is transmitted across the membrane, and this is called as an impulse. So let us, before going on into the details of the action potential, let us see what is the meaning of the resting potential. Now all the membrane, all the excitable tissues in the body, let us take the nerve or the muscle, has got an electrical charge across the membrane. Now, this electrical charge which is present across the membrane is because of the difference in the ionic concentration of the membrane of the substances across the membrane. We know that the sodium concentration outside is somewhere around 142 milliequivalents and the concentration inside is around 14 milliequivalents. Similarly, when we see the potassium concentration is the reverse way out, where the concentration of potassium inside is more and it is less outside. Now both the sodium and these potassium ions are having charges across it, and they are both positively charged ions. In addition to this, we also know that the inside of the cell membrane, whether it is a muscle membrane, muscle tissue, or a nerve tissue, or a normal ordinary cell, the inside of the cell consists of large molecules of proteins and amino acids. These proteins and amino acids are negatively charged and they cannot pass across the membrane. So now this difference in the ionic concentration between the outside and the inside normally makes the cell inside more negative than the outside. So if you place a voltmeter and place one of the electrode in the inside and another electrode on the outside and see the difference in the potential, you will find that this potential inside is around 70 millivolts negative than the outside. So we call that this 70 millivolt, that is minus 70 millivolts, as the resting membrane potential. It is called as the resting membrane potential because it is the time where the nerves or the muscles are not active or are under resting conditions. So the potential which is measured or which is there across the membrane when the nerve or the muscle or the cell membrane or any excitable tissue is not active or is not transmitting any signals is minus 70 millivolts, and it is called as the resting membrane potential. Now briefly I will tell you how is this resting membrane potential developed. Now when we see the ionic concentration, as if you see on the slide there, it will clearly explain to you, it will clearly self-explanatory that on the outside there are more sodium ions and in the inside there are more potassium ions, and in addition to this they have got certain other negative charge which is chloride ions. Now the resting potential is because the concentration of the ions on different sides of the on the two sides of the membrane are different. Say for example, the sodium and the chloride ions are more on the outside, whereas the potassium and the organic anions are more inside the cell. Now let us see how this resting membrane potential of minus 70 millivolts is developed across the membrane. To understand this, we have to first understand that the membrane is permeable to most of the ions. It is permeable to sodium ions, it is permeable to chloride ions, it is permeable to potassium ions, it is permeable to bicarbonate ions. The permeability of this membrane is different at different times. That means under resting conditions, the membrane is permeable to sodium ions. The sodium ions can move across the membrane from outside to inside freely. Similarly, the membrane is also permeable to chloride ions, and the chloride ions can also move from outside to inside, that is diffuse from outside to inside because of the concentration gradient. The potassium ions can also move from inside to outside or diffuse from inside to outside because there is a diffusion potential existing from inside to outside. Now, the membrane being permeable to multiple ions, let us consider one by one how the contribution of each individual ion helps in the development or in the build-up of the resting membrane potential of minus 70 millivolts. Now, for a moment, let us assume that the concentration of the sodium ions being more outside and less inside, and the membrane is permeable only to sodium ions. So hypothetically, we are assuming that the membranes are permeable to sodium ions. The concentration of the sodium ions outside is 142 and inside is 14. The membrane now is permeable to sodium ions. It allows the movement of sodium ions from outside to inside. Now, as the sodium ions are moving from outside to inside, they are carrying a positive charge from outside to inside. When they carry a positive charge from outside to inside, the potential inside, which is electronegative becomes less and less electronegative. Now, ideally, this diffusion should happen from outside to inside till the concentration of the ions on both sides for sodium ions become equal. But remember here that the sodium ions, when they are moving from outside to inside, are not simple sodium ions, but they are also positively charged ions. So when these sodium ions are moving from outside to inside, they are also carrying along with it a positive charges from outside to inside. When these positive charges are coming inside the cell, there is buildup of positive ions inside. There is more and more electropositivity inside. That means the minus 17 millivolts potential is becoming less and less electronegative, and the potential after moving from minus 70 will go to minus 30, minus 40, minus 40, minus 30, minus 20 and 0, and this will go on till it reaches a potential of, say, let's say around plus 20 millivolts. Now at plus 20 millivolts of positivity inside, the membrane suddenly becomes impermeable to sodium ions, and the diffusion of sodium ions from outside to inside stops, despite the fact that there is still a diffusion concentration gradient available from outside to inside. Though there may be a diffusion potential still existing from outside to inside, but because of the development of electropositivity inside at plus 20 millivolts, the membrane suddenly becomes impermeable to the sodium ions. Though a concentration gradient may exist for sodium ions for movement from outside to inside, and this potential at which the membrane becomes impermeable to further diffusion of sodium ions is called as the Nernst potential for sodium ions. I hope this is clear. I will explain it to you again. We start from the basics again. There are certain excitable tissues in the body. The most excitable tissues are the nerve and the muscle tissue, plus the other membranes are also permeable, but they are little less excitable. Now we also know the second fact is that there is more concentration of sodium outside and less inside. Because of this difference in the difference in the concentration of ions, there exists a potential for sodium ions to move from outside to inside, that is diffuse from outside to inside in the direction of the concentration gradient. So the gradient for movement of the sodium ions purely on the basis of the numbers is from outside to inside. Now let us assume that this cell membrane, which is selectively permeable, suddenly becomes permeable to sodium ions only. So if this membrane becomes permeable to sodium ions only, it will allow the diffusion of sodium ions from outside to inside through these sodium channels. Now as the sodium is moving from outside to inside, by pure laws of diffusion, this diffusion of sodium ions should occur from outside to inside till a concentration gradient becomes equal on both sides. That means till an equilibrium is reached. So the concentration, which is now before the diffusion at 142 on one side and 14 on the other side, so much of sodium ions should diffuse till the concentration of sodium ions on both the sides of the membrane become constant or become equal. But you should also remember here that when sodium ions is coming from outside to inside, it is carrying some positive charges along with it in the inside. So this movement of sodium ions is not only pure ionic movement, but some charges are also moving from outside to inside. So there is a buildup of positive ions inside the cell and loss of positive charges on the outside of the cell. Consequently, when each sodium ion is moving towards the inside, because of the diffusion of sodium ions, there is a buildup of positive charges and the membrane potential and the potential inside the cell, which is normally minus 70 milliequivalents, becomes less and less electronegative because of the positive ions, that is the positive sodium ions inside. So now this membrane in the potential inside the cell starts becoming slowly less and less electronegative, that is, which is normally at resting condition minus 70, it becomes around minus 40, minus 30, 20, minus 20 reaches 0, and if still this diffusion is going on of sodium ions from outside to inside, the potential becomes positive. From 0 it becomes plus 10, plus 20, maybe plus 30. At plus 20, suddenly when there is a plus 20 electropositivity inside, the membrane suddenly becomes impermeable to the sodium ions, though still a concentration gradient may be there for the sodium ions from outside to inside. So despite a concentration gradient existing for the movement of sodium ions, because of the electropositivity of plus 20 millivolts inside, further diffusion of the sodium ions does not take place. This potential at which the sodium ions inflow does not occur because of the buildup of positivity, this potential is called as Nernst potential for the sodium ions. This can be explained by the Nernst equation. Now let us think that at some point of time the membrane now becomes permeable to potassium ions only. So now the potential for the sodium ions does not exist. The membrane is becoming permeable only to potassium ions. Now, if the membrane becomes permeable only to potassium ions, there is a diffusion occurring for potassium ions from inside to outside. Why is there a diffusion occurring? Because the concentration of potassium inside is more than outside. Now the membrane is permeable to potassium ions only, and the potassium ions will start moving from inside to outside. That is, so potassium channels will now allow the potassium ions to move from inside to outside, which is the direction of the diffusion concentration gradient. Now, as potassium ions is moving from inside to outside, according to purely the laws of diffusion or the diffusion laws, this movement of potassium ions from inside to outside should happen till an equilibrium is reached, or that is till the concentration of potassium ions on both sides of the membranes become equal. But it is not that the potassium itself is purely a number ion, it is also carrying certain positive charges from inside to outside. So which each diffusion of potassium from inside to outside, there is a loss of positive charges from the inside to outside. So now with this loss of potassium charges, positive charges from inside to outside, the membrane now becomes more and more negative inside. So this diffusion of potassium ions is occurring in the direction of the concentration gradient, and this occurs till the concentration reaches a level where the electronegativity inside the cell reaches minus 61 millivolts. When it reaches minus 61 millivolts, further diffusion of potassium ions will stop from inside to outside, though a concentration gradient is still existing for the potassium to diffuse from inside to outside, and this potential of minus 61 millivolts at which further diffusion of potassium ions will stop is called as the Nernst potential for potassium ions. So now we have got two Nernst potential, one Nernst potential for sodium ions, another Nernst potential for potassium ions. Similarly will be the Nernst potential for chloride ions, assuming that the membrane is permeable only to chloride ions but is not permeable to sodium ions and potassium ions. So either the Nernst potential for sodium ions or the Nernst potential for potassium ions is that potential at which further diffusion of the ions stops despite a concentration gradient still existing across the membranes. Now let us see if the membrane becomes permeable to all sodium, potassium and chloride simultaneously. We know that small amount of potassium ions keep diffusing across, sodium ions is strictly impermeable, but still there are certain leaky channels which allow the sodium ions to move. The chloride ions also can diffuse from outside to inside apart from the channel or the membrane channels allowing potassium to move. So now if you assume that the membrane is permeable to all three ions, sodium, chloride and potassium, then what will be the membrane potential? And that membrane potential is explained by the Goldman-Katzkin equation, and that is the resting potential of the membrane, and that is somewhere around minus 70 millivolts. That is, if we extrapolate the fact that there is some sodium ions which is leaking, there is a potassium ions which can move across the membrane, chloride ions are also getting diffused, bicarbonate ions can also move. So what is the ultimate potential which is present inside the cell when the membrane is not actively not transmitting any movement of ions across the membrane? Active transport is not taking place. That is the resting membrane potential, and that is around minus 70 millivolts. So Nernst potential for sodium ions is purely 20. Thereof for potassium ions is minus 61. All the three ions is explained by the Goldman-Katzkin equation, and the resting membrane potential then works out to be at minus 70 millivolts. So what is this resting membrane potential? Resting membrane potential is the potential which is present inside the cell when the membranes are not actively transmitting any impulses or not actively allowing any ions to move across the membrane, but small amounts of ions like the potassium ions can move across the membrane, plus sodium leaky channels are there and chloride can also leak to the cell membrane. So this is about the resting membrane potential. Now because it is minus 70 millivolts, there is a electrical charge which is present on the inside. The electrical charges, if you see, is more inside than the outside, and this potential is called as the resting membrane potential. Different excitable tissues may have different resting membrane potentials. For a neuron, the resting membrane potential is around minus 70 millivolts. And a resting neuron means a neuron when it is not firing, and when it is not firing, it means that it is not transmitting any signals across the membrane. That means that no action potential is getting transmitted across the membrane. Now here this is the resting stage. Here you will find that there is an active movement taking place, where you will find that there is a sodium ions which is coming from outside to inside, and there is a potassium ions which is going from inside to outside. So in such a condition, when there is a small amount of sodium ions which are diffusing from outside to inside because of the leaky channels, and potassium can also move from inside to outside, at this potential of minus 70 millivolts, there is no active movement of ions taking place, and the concentration of the sodium ions and the potassium ions is maintained clearly. Imagine if this potential did not exist, what would happen? If at this potential the diffusion of the ions does not stop, you will find that there is a constantly movement of sodium ions taking place till the concentration becomes equal on both sides. The concentration of potassium ions or diffusion of potassium ions moving across the membrane till an equilibrium is reached, or till the potassium ions become equal on both sides of the membrane. That will become totally unstable membrane, and there will be total mismatch of the charges across the membrane. Hence the nature has provided a electronegativity of minus 70 millivolts, where at this point in any cell, in any muscle or any nerve, no active transport of substances can take place, and hence the concentration of the ions also remains constant. So it is because of this resting membrane potential, the electronegativity charges is maintained, and also the constancy of the internal environment is maintained. And what do we mean here by constancy of the internal environment? Means the concentration of sodium outside 142, inside potassium 14. Similarly, the concentration of potassium inside is somewhere around 135 to 140 milliequivalents, and outside it is around 42 milliequivalents. So this is the importance of the resting membrane potential. Now with this in background, let us see what are the changes which are taking place when a nerve is disturbed, or a muscle is stimulated, or when any cell membrane is disturbed or stimulated. So that changes. So the rapid changes in the membrane potential, where a membrane depolarizes and repolarizes, is called as action potentials. So this action potential is a change in the membrane potentials because of the excitable nature of the cells, resulting in disturbance in the ionic concentration. And once this whole process is completed, that particular change in the concentration is known as an action potential. Now, what do you mean by action potential? First of all, action potential is nothing but sudden rapid changes in the membrane. When does this rapid change in the membrane takes place? This rapid changes in the membrane takes place specifically whenever there is a excitable membrane, excitable tissue. And what do you mean by excitable tissue? Excitable tissue means the tissues which which respond whenever there is a stimulus given. And what is the meaning of a stimulus? Stimulus is a change in the external environment. So remember this carefully. All these things are linked, and you should know the definitions. What is action? First, what is membrane potential? Membrane potential is the potential across the membranes when the membrane is in resting condition. What is action potential? Action potential is changes in the membrane potential whenever the membrane is excited. What do you mean by excitability? Excitability is the ability of the membrane to respond to a stimulus. And what is the stimulus? Stimulus is a change in the external environment of the membrane. So what can be a change? To give you a simple example, suppose you are pricking yourself with a pin on the tip of your finger. So what happens whenever you prick a pin in the tip of a finger? or you put your finger on a very hot water, on a hot object, immediately you respond. Till that happens, the nerve is resting. When you give a pinprick, this pinprick is penetrating your skin and changing the environment, external environment across the membrane. This is called as the stimulus. The ability of the nerve to respond to this pinprick or to respond when you put your finger on a hot object is the excitability of the membrane. And when this excitability, why is this excitability there? Because it is responding to the changes. And what changes is responding is the action potential. Let us see the difference here. All the cells have resting membrane potential, but only excitable cells like nerve and muscles are capable of producing an action potential. Now, before the action potential begins, it is known as a resting membrane potential. At that point, the membrane is said to be polarized, and the polarization is around minus 70 milliequivalents. So, what happens whenever there is an excitability occurring? Now, the excitability means the ability of the membrane to respond to change in the environment. So, any factor which causes a change in the external environment is called a stimulus. So, suppose you are giving a pinprick, or you are touching a hot object, or you are giving an electrical change. You are causing a disturbance in the external environment. This disturbance in the external environment will make the membrane permeable, and it will make the membrane permeable to the sodium ions. So, as soon as a stimulus is given onto the nerve or to the muscle, the membrane suddenly becomes permeable to sodium ions. So now let us see the changes, let us explain and understand the graph along with the changes which are happening here. So here let us say the excitable nerve or the membrane or the muscle is under resting condition. The resting condition, at this resting condition, the potential is around minus 70 millivolts. A stimulus is given. When the stimulus is given on the nerve or the muscle, the membrane suddenly becomes permeable to sodium ions. It allows the sodium ions to open, sodium channels to open. When the sodium channels open, it allows the sodium ions to move from outside to inside. When the sodium ions are moving from outside to inside, the positive charges are coming in. The resting membrane potential now slowly builds up from minus 70, and as more and more sodium ions keep coming inside, the electronegativity becomes less and less and reaches a potential of around minus 55 millivolts. If you see the diagram and try to analyze the diagram here, see one here, this is the on this x-axis you have the time factor, on this axis you have the potential. From this point to this point, let us say it is around 10 to 20 milliseconds. So as the stimulus is given, slowly in the next 20 milliseconds, you will find that the membrane potential changes from minus 70 to minus 55 millivolts. This change in the potential is called as the generator potential. So from minus 55, minus 70 to minus 55, it takes around 20 milliseconds for the generate potential to change from minus 70 to minus 55, and this is called as the generator potential. Once it reaches minus 55 millivolts, suddenly there is a burst of opening up of the sodium channels. Hundreds and thousands of sodium channels open up. Because of this opening up of so many channels, sodium ions move from outside to inside, and within a few 1 or 2 milliseconds, if you note here, suddenly the membrane potential changes from minus 55 0 to plus 35 millivolts. So at this point, when it reaches plus 35 millivolts, this phase is called as the depolarization phase, and this potential of minus 55, when there is a sudden opening up of the sodium channels, is called as the threshold potential. Now, because there is sudden opening up of the sodium channels within a few milliseconds, 1 or 2 milliseconds, the potential inside becomes less negative from minus 55 to 0, from 0 to plus 35. At this point of time, this phase from the threshold potential to plus 35 is called as the phase of depolarization. Now at plus 35, two things are happening. Once, remember the nest potential for sodium ions. At this potential, you will find that at plus 35 millivolts, you will find that the further diffusion of sodium ions will stop. So suddenly you will find that when the membrane potential has reached at plus 35, though there is a concentration gradient existing from sodium to move from outside to inside, but it will close all the sodium channels. Because the sodium channels are closed, the potential does not becomes more positive and stops at plus 35 millivolts. At plus 35 millivolts, another change is happening. The potassium channels begin to open. Now, once the potassium channels begin to open, the diffusion of potassium ions will take place from inside to outside. When it goes from inside to outside, it is causing the positive charges to move from inside to outside. There is a loss of positive charges from the inside, so this brings down the positivity inside. As a consequence, you will find that this loss of potassium or positive charges from inside to outside brings the membrane potential down from plus 35 to 0, from 0 to minus 55, and at that time you will find that the potential reaches back to the resting membrane potential of minus 70. So this phase from plus 35 to minus 55 and to minus 70 is called as the repolarization phase. Once it reaches minus 70 millivolts, one thing will happen here is the potassium channels now will begin to close slowly. As they close at this point of time, the action potential comes to back to normal, and sometimes you will find that the potential goes down below minus 70 to somewhere around minus 75 or minus 80. This phase is known as the hyperpolarization phase, because some potassium ions remain open for a longer time. So more amount of potassium ions would have diffused from inside to outside, causing the potential to fall less than minus 70. So that phase is called as the phase of hyperpolarization. After a few brief milliseconds, all the potassium channels close and the action potential comes to an end. So this is the genesis of action potential, where you will find that a stimulus is given, the resting membrane potential moves from minus 70 to minus 55. This is the generator potential. At minus 55 millivolts, you will find that there is a sudden opening up of the sodium ions. The sodium ions move towards the inside, so positivity is coming inside. So the potential starts moving in a few milliseconds from minus 55 to 0 to plus 35. At plus 35, two things are happening here. The sodium ions close, the potassium ions open. When the potassium ions open, The diffusion of potassium ions takes place from inside to outside. When the potassium ions are going from inside to outside, you will find that it is carrying positive charges from inside to outside. So there is a loss of positivity and the potential falls from plus 35 to 0, and it ultimately becomes so much so that it reaches back to minus 55 and slowly over a period of time to minus 70. This phase is called as the repolarization. At minus 70, you will find that the potassium ions close, potassium channels close. So further diffusion of potassium is not taking place, but few potassium channels are little slow to close. They take more time to close. So the potential may marginally dip down to minus 75 or minus 80. That phase is called as hyperpolarization, and ultimately after some time this reaches back to once all the potassium channels have been closed, the electronegativity restores back to minus 70, that is the resting membrane potential. So the whole genesis of the action potential is there is a generator potential, there is a threshold potential, there is a phase of depolarization, there is a phase of repolarization, there is a phase of hyperpolarization. All this constitutes the action potential. Channel wise, let us explain to it in terms of channels. Till now explained to you in terms of potential. Now in terms of channel, here you will find that there is the membrane in resting membrane potential is closed to, is resting membrane potential is impermeable to sodium ions. A stimulus is given. The stimulus can be a chemical stimulus, you put some chemical, or it can be electrical stimulus, or it can be a physical stimulus. At this point of time, when a physical stimulus is given, the membrane becomes suddenly permeable to sodium ions only. So sodium ions open. So this opening causes some sodium ions, positive ions to move inside. So at this point of time, when it reaches the threshold potential, hundreds of sodium ions are opening up, and this causes the potential ions to move. The sodium ions continue to move from inside to outside, takes the potential to plus 35. At plus 35 millivolts, two things are happening. The sodium channels close and the potassium channels open. So once at this point the potassium channels are open and the sodium close, further electropositivity does not happen, but now the potential starts falling down because of the loss of positive charges from inside to outside. So positive charges are lost from inside towards outside, so it becomes less and less electropositive, and there is a electronegativity developing inside. This is called as repolarization. So as the potassium channels keep opening, potassium diffuses from inside to outside till it reaches minus 70 millivolts. At minus 70 millivolts, the potassium channels close. So further diffusion of potassium ions does not take place. The resting membrane now stabilizes at minus 70, but for a few milliseconds, some potassium channels which are slow to close remain open for a millisecond, and they cause the potential to drop to minus 75 or 80. This is hyperpolarization. But after a brief milliseconds, you will find, after some more time, you will find here that all these potassium channels have closed and the resting membrane potential is restored back to normal. So this is about the action potential. Now once this action potential is generated at one particular type of nerve, at one particular point of the nerve, this is transmitted all across the whole of the nerve, and the transmission of action potential takes place. The impulses go allwards to the brain, and then you respond either reflexly or consciously, that whenever there is a pinprick, you feel that there is pain, you withdraw your hand. Whenever you touch a hot item, and when you immediately respond. So the body responds to this action potential, because though the site of injury or the point of injury may be the tip of the finger, but the whole hand is moved, because action potential travels all along the length, goes to the spinal cord, and reflexly you withdraw your hand. This is how the transmission of impulses takes place, and this is because the nerve tissue is excitable. So the action potential is a function of the excitable tissue. Now hope you have understood here what is the genesis of membrane potential, why the membrane potential is at minus 70 millivolts. This minus 70 millivolts is under resting conditions, hence it is called as a resting membrane potential. I have explained to you what is the nurse potential for sodium ions, what is the nurse potential for potassium ions. I've also explained to you, if the membrane is permeable under resting condition to all the ions, then the resting membrane potential is explained by Goldman-Kasking's equation, and that brings the resting membrane potential to minus 70 millivolts. Then we have seen what is excitable tissue. We have seen what is the definition of an action potential, what is the definition of excitable membrane, what is the definition of a stimulus, what is the genesis of action potential, how the action potential is developed and it comes to an end, what are the components of the action potential, namely the generator potential, the threshold potential, the phase of depolarization, the phase of repolarization, and the phase of hyperpolarization. But if you concentrate here, you will understand that because of this action potential, sodium ions from outside have come inside, that is in depolarization, and during repolarization, the potassium ions have gone from inside to outside. This, as a result of this action potential, one of the things which happens is the disturbance in the concentration of the sodium and the potassium ions have taken place. Normally, the sodium ion should be 142 milliequivalents outside, but because of depolarization, some sodium ions have come inside the cell, and because of the repolarization, the potassium has gone from inside to outside. That is, the concentration of potassium should be 142 milliequivalents, but because of the action potential during the phase of repolarization, some potassium has moved from inside to outside, as a result of which there is a disturbance in the sodium concentration and the potassium concentration across the membrane. Now you have to go back and read how is this disturbance or this change in the concentration of sodium ions and potassium ions brought back to normal, so that the homeostasis is retained and the concentration of the sodium and the potassium ions is restored back to normal at the end of the action potential. All of you go back and read the books. There were some doubts about which books to be followed. In my first class, I had explained at the end of the session, I had given a PPT diagram, PPT of the pictures of the books. Again, I am repeating it. You can follow any one of the three books. One is the textbook of physiology by Guyton and Hall. The second is textbook of physiology by Dr. D. Venkatesh, or the textbook by physiology by G. K. Pal, which has got two volumes, volume 1 and volume 2. So go back, read this. When you come back in the offline course, we shall have a small group discussion and I shall ask you the answers for all these questions which I have asked you today. And in the earlier class also, during the action potential, during the active transport, I had asked you about some questions which we can discuss it later in the offline part. Thank you all of you. Have a good day.